Good morning. We're going to start Focus 4, which is talking about what we've learned about thermodynamics and Gibbs free energy and how it relates to physical transformation. So phase transitions. So we'll start with equilibrium in phase transitions, and then we'll finally end up in chapter 5 or Focus 5 with equilibrium and chemical reactions. First, we need to learn some new terminology and just some concepts. So I'm going to plug in the camera. Okay, so this is Focus 4. And okay, I'll mostly work on paper this morning. So we're going to learn about the thermodynamics of transitions. And in the next section B, we'll learn about phase diagrams of pure substances. Then we'll talk about partial molar quantities. So how does Gibbs free energy change will be our main focus, which will come out to be the chemical potential as you change the composition, change the number of moles of substances. And then we'll talk about making solutions and move from there into colligative properties. And we're going to skip the section on phase diagrams of mixtures, not because it isn't interesting, but we need to skip something or we're not going to make it through the whole chapter. So the thermodynamics of a transition. So talks a lot about just what kind of things you're thinking about. So you can have solid to liquid fusion, you can have liquid to gas vaporization, you can have solid phases, different solid phases like diamond and graphite, changing from one phase to the other. And so we're going to be focused on Gibbs free energy. So the key idea in this very first section is that a substance tends to adopt the phase with the lowest molar Gibbs energy. And you really want to think about that. We derived this earlier. That a change in Gibbs free energy is really related to a change in entropy of the whole universe. So the total change in entropy as a result of a process. Because T is always constant, it's absolute temperature, that means if the molar Gibbs free energy is going down, the entropy of the universe is going up. So the key idea really is the second law of thermodynamics. We've just created a function that relates to the total entropy, so it makes it easier for us. You want to remember that it's only at constant temperature and pressure that these relationships are true. So if this is less than 0, then it's spontaneous. Equals 0, we're at equilibrium. And it's non-spontaneous. If you say it's non-spontaneous, it's spontaneous in the reverse direction. So these are the ideas we're going to use, but we're going to think about them in terms of, will it be spontaneous for a liquid to become a gas or gas to become a liquid? Or are we at equilibrium where we have a gas and a liquid in equilibrium with each other? So we're going to focus on the Gibbs energy and in general talk about the molar Gibbs energy because we're talking about different phases. And so reminds us how we would get a delta G. It would be the delta G difference between second phase and the first phase. So if we're talking about gases, the second phase, it'd be the molar Gibbs free energy times the number of moles that leaves the gas phase minus the Gibbs free energy, for example, of the liquid, if that's a transition we're talking about, and the number of moles that enter the liquid, and that's our delta G. So a substance has a spontaneous tendency to change into the phase with the lowest molar Gibbs energy. So that's exactly our key idea. So go ahead and take a break and do this self-test. Self-test 4A.1. It's very much a Gen Chem question. So how does the Gibbs free energy change with temperature and pressure? We usually think about phase transitions as being spontaneous or in equilibrium at different temperatures, and also it depends on the pressure. So we're gonna derive some relationships that relate those to each other. And this first one is a very common thing to do in thermodynamics. So we are going to derive this relationship. Gibbs free energy change is proportional to the molar volume times the pressure change. And really it's this second equation that's the one that we want to use, because the first one is only true if the volume stays constant with pressure. So that's pretty much for liquids and solids. So we want this more general expression. And where does it come from? Expect to do something like this on the test because it's such a common and important concept. So if we start out with the definition of the molar Gibbs free energy, Gibbs free energy is enthalpy minus Ts. So that they show you right here in this justification. And so now we want to take that into a differential and then figure out how in the heck do you get volume and pressure into this function that starts out as a function of enthalpy, temperature, and entropy. So the first thing we want to do is, and I'm going to drop the molar because this would be true whether it's molar or not. So if Gibbs free energy equals H minus Ts, then an infinitesimal change is also equal to each other. And so because these are state functions, by expanding that differential, what we're saying is it doesn't matter if we change them at the same time, or if we change entropy first, holding temperature constant, and then change temperature, holding entropy constant, or you could reverse these two terms. So the path in which we go from a TS to a TS2 is independent of, well, it's independent of the path. So that means I'm choosing this path where I hold one constant and change the other one. The other thing we know is that enthalpy is U plus PV. So now let's put all of that into our equation. So that means dG is equal to du plus, I can do the same thing I did here. A change in PV, if these are both state functions, can be written as a change in each of them separately, holding the other constant. So minus T delta S minus S delta T. We're getting there. Now we want to think about what we learned earlier about du. du equals Q plus W, so it equals the heat transfer and the work done. We also know that if you choose a reversible path, then T ds equals dq, and P dV equals dW. So infinitesimal work, whoops, it's a negative in front of that, is equal to negative PdV, and TdS is equal to dQ. So this is true if it's a reversible path, but something very subtle. Doesn't matter which path I choose, the change in Gibbs free energy is independent of path. So I can pick a reversible path and I can carry out the process irreversibly, but the change in Gibbs free energy would be still equal because it's independent of the path I chose. So now I can have a whole bunch of things here. So it's going to be TdS minus P dV, that's my du, and then plus P dV plus V dP minus T ds minus S dt. And we're close. So now let's see what we can cancel. So we have minus PdV plus PdV. We have TdS and we have minus TdS. And so we end up with dG equals V dP minus S dt. And now we can think about the situation that they're talking about first, which is we only change pressure, we don't change temperature. So then dG equals V dP. And so if you look at that, that's the equation we started with. The general form, where it's still an infinitesimal change, you can then derive an expression for a change in Gibbs free energy for solids and liquids, and then also for gases. So if we have solids and liquids, then integrate on this side. So volume for solids and liquids is pretty constant with a pressure change. So a dG can be just integrated to be constant molar volume times delta P. So that's the first equation they give you. What happens if it's a perfect gas though? So then it's still going to be dG, but when I look at this, V is a function of P. So for gases, V equals nRT over P. And so if I put that in, if it's molar, then it's RT over P dP. And so when I integrate that, you get RT. And this will be an integral you'll do over and over and over. 1 over x, the integral is natural log. So you get RT ln of P2 over P1. So because volume isn't constant as you change the pressure of a perfect gas, we have to integrate. If you had a different functional form, if you knew your gas wasn't behaving ideally, you could put in the van der Waals expression for volume. So for liquids and solids, generally, unless you're really dealing with an extreme pressure change, the volume will stay constant. For gases, you have to worry about gases' pressure does impact their volume, so you have to integrate over it. So let's look at this equation. So the equation really tells us from the start is that the slope of a line that's relating Gibbs free energy change to a pressure change is really equal to the volume. So when you look at this graph, it's showing you that gases have a much larger volume than solids and liquids. And you'll have points at which these lines cross. So where the molar Gibbs free energy of the liquid and solid are equal, that's the phase transition. That's the point at which liquids and solids would be in equilibrium with each other, gases and liquids, gases and solids. So that graph is to show you that generally gases have a higher molar volume, so they're going to have a bigger change in Gibbs free energy with pressure because that's the relationship. So go ahead and do this self-test. For 8.2. You'll have to use these two equations, but I don't think it'll be too challenging for you. So self-test for 8.2 and then come back. And here's the equation I derived. I don't know why they had you use that equation and then they derive it for you. So they went through the derivation here. And then they talk about how does molar Gibbs free energy change with temperature. Well, if we go back here, we derived this equation right here. So now if we're saying the pressure is constant, but only the temperature is changing, then we're going to have a similar situation that will tell us that the Gibbs free energy change is equal to a minus entropy dt. So now the slope, the relationship between the Gibbs free energy change and the temperature change is equal to negative entropy. So there's another graph on the next page. Yeah. So this is just showing you that relationship. So as you change temperature, you're going to reach points where the lines cross each other. So gas has more entropy than liquids and solids. Liquids tend to have more entropy than solids. So the slope of the line for the gas changing its Gibbs free energy with temperature is much steeper. The liquids line is in between, and then the solid is the smallest slope. So you're going to see points at which these lines cross, and those are going to be the temperatures of those phase transitions. The other graph showed you if you were holding temperature constant, what pressure would the phase transitions take place. This one is now telling you at what temperatures the phase transitions will take place if you're holding pressure constant. And I assume, they don't say it, but that this graph is at 1 atmosphere, or in your textbook, sorry, 1 bar is your standard pressure. So this is just exactly the same graph. And just what I just talked about with it, how you can look at this, the slope of the lines and know that's because the entropies are different. Then you can look at the points at which they cross each other. Those are the points at which you're going to have phase transitions. You can take that equation that relates temperature to a Gibbs free energy change, and you can derive this equation, which is called the Gibbs-Helmholtz equation. That's one of the things you can wait and do in 366 if you want to take more thermodynamics. And so that is it. If we need to use this equation, I think in the next focus where we look at how Gibbs free energy changes for reactions with temperature, this will allow us to figure out how an equilibrium constant changes with temperature. It'll be related to a delta H. So before you quit, make sure you do this last self-test. So this is 4A.3, kind of blurry on my copy here. So go ahead and do that one. And that is all of this first section. The second section, 4B, takes us now into just looking at pure substances. And we know that the phases are going towards having the lowest Gibbs free energy. We can think about where the boundaries are in making our phase diagrams. So read through this one, and it will use the equations that we just derived. Think about those, and then we will just look at, yeah, I'll do a short lecture on the first part of the chapter, and then I'm just going to have you put the phase diagrams on the board. So when you're looking at B, know that I will go through a short lecture on the first few pages, and then when you get to the section on characteristic points, that's just reminding you of a bunch of definitions, things like the triple point, the critical point, and it gives you some examples of different phase diagrams. So when you get to section 4B.3, just be ready, I'll have you guys put those on the board. but I will do a lecture on the first section for you. So that's it for 4A.